So are there any questions over stuff we've done? If not, I think we might want to just jump into this homework because it is fairly lengthy. So exercise 3, we want to use the graph to solve f of x equals g of x. And then we want to solve this thing symbolically. Okay, so if we're solving an equation with two functions, what is our solution going to look like? What are we looking for? What does the solution look like graphically? Have we talked about that? I feel like we have, but it's been a minute maybe. If we want to know where this thing is equal to this thing, where would that be?
Where they intersect each other?
It's the inner point of intersection. And so if I'm solving this thing, what am I interested in? Which quantity am I interested in?
The y value?
The y value is going to be where at 2.5. What does the solution look like? If we do it symbolically, maybe that'll help. If we do f of x equals g of x, how will we find a solution to this symbolically? So what do we know about f of x?
F of x is it's a curve line. It's like I forgot what the word is where it curves. It's not a straight line.
Yeah, but symbolically, what does it look like?
It's a
How would I write it symbolically?
what is that called? Exponent. Yeah.
How would I write it? Is there another
Looks
way
like
I can write
log
it?
or something?
Is there another way that I can write this? It's
10 to the x.
I can write it as 10 to the 0.2x. I can rewrite g of x as what?
2.5.
2.5. And so if I want to solve this thing symbolically, I know what the function sort of looks like in terms of x. And if I solve this thing, what am I solving for? What variable am I solving for?
X.
I'm solving for my x variable. So what variable I want to look at is my x variable. So if I want to solve this thing graphically, it's going to be the x quantity that I'm looking at. If I want to do this thing symbolically, I have it set up to solve symbolically. And I think this might have been the question you were answering a while ago. If I have 10 to the 0.2x equals what, 2.5? This thing is an exponential function. So the first step is to get the exponential by itself. I see a head nod. So I think this thing is already by itself. So if we want to get rid of this thing, how would I get rid of a 10 to the 0.2x? How would I get rid of the exponent or the base here? How would I undo this thing being exponentiated, right?
Take a log.
All right, so we're going to take a log of both sides. And if I take a log of both sides, what do we notice about this side?
The 10 cancels.
These two things should simplify. And so what should this left side be equal to?
0.2x.
Yeah, 0.2x. And this is equal to log of 2.5. And we want to solve for what variable?
X.
We want to solve for x. So what's the last step I have to do? They give you.
And divide by 0.2.
Yeah, I have to divide by 0.2. So x is going to be log of 2.5 divided by 0.2. And if I want an exact solution, this is it. If I want to see like how this compares to that thing that's on my graph, you might notice I probably just said x equals 2 over here, but it really is not just an exact 2, right? It's like some fractional amount. It's going to round to 2, right? It's a round 2. 9897. So this is why you don't want to solve things graphically again, right? You definitely want to solve things symbolically if you can. But if this was a model, right, and depending what we're modeling, 2 might be good enough. Like we're talking about a really fractional amount. It kind of depends what you're doing sometimes, to be
If
honest.
you're doing it on a graphic calculator or Desmos, you could get a pretty accurate answer.
Yeah, but I was just thinking like in realistic like applications of this
Yeah.
thing. Like if you're talking about 2 years versus 1.9897 years or something like that, right? Like that's not going to be a whole lot.
Right.
Yeah. Like,
Unless you're talking about brain surgery or
yeah.
rocket science.
Yeah. Like I said, it like kind of depends what you're applying it to. All right. So we got these two things. I want you to spend a good minute to do these. I showed one way in the notes. There are multiple ways to do these things. I like to take logs of weird bases. Some people don't like to do that. It doesn't bother me none because I got a calculator. We're at 9:14. Okay, so the strategy with solving these things, and I kind of said it, is to get the weird thing by itself. So if you see an exponential, get the exponent sort of thing by itself, right? I think 9, that's already done for you. 13, you might have to do that a little bit. And then we want to undo the exponent. So that's going to be probably like the quote unquote hard or difficult, the extra step they added in this section, right? Okay, so like most of your time, your solution for these things is gonna look like weird logs and stuff like that. Like, unless it says to round it, right? We typically want exact solutions for these things. With that said,
And on the test, I'll ask for the exact and the, well, we will ask for the exact and then also the approximation so sometimes your exact solution might not look exactly like our exact solution, but the approximation should look the same.
okay, so we get 2 to the x plus 3 equals 128. So this thing is the exponent. This is the base and this is the exponent. So this is my exponential, I want to say function. Yeah, function happening out here. How do I undo this thing? This is a base 2. What do I do to undo a base 2?
You can do a log base 2.
This is exactly how I'm going to do it. So there is another way you can do this, and I'll probably show you right after this. It's very similar. So I'm going to do log base 2 of 2 to the x plus 3. I'm going to do a log base 2 of the other side, which is 128.
This is my favorite way too.
All right, so now that I have this thing written, is there something on this left side you notice? We have a log base 2 and a 2 to the something. Hoping that is the reason why you took the log base 2. Those two things should simplify. So what should be on the left side?
Just x plus 3.
It should be x plus 3. And this should be, is that something that's even log 2? I think it might be, yeah, okay. $128 is 2 to the 7th. So there are a few ways to do this one. I would probably do the change of base and just put that in my calculator if I'm being honest. 128 is not something that just pops in my head really regularly. I guess it's what, twice 64. But there are several ways to crunch this thing. Log of 2 of 128 should give you what number? I think I said it already, huh?
7.
All right. And we're getting what, x plus 3 equals 7. X is equal to 4. Are we following along? Are y'all attempting these and getting them? Let's see, one head nod. Okay. The other way that people will do these is they won't take a log base 2 for some reason. They only like taking logs.
That's how they teach it in high school.
Yeah, I don't like doing this as much.
I don't either.
If we just take a log base 10 of things, we can use that exponent property that y'all love so much. We can bring this thing down in front. So we have like an x plus 3. We have a log base or log base 10 of 2 and a log of 128. If I'm solving for x plus 3, the first thing I'm going to do is going to be divide by this log 2. And if you notice, when I do that, I basically have this back at that step where I did the change of base. So it like becomes that other problem at this point, basically. So if you don't like taking logs of weird bases, you can always do log base 10 of things and then use this exponent property to bring things down. But like this to me has more potential to mess up because this has some distribution you have to do here. So you have to be sure to put your parentheses around this thing. I don't know. To me, the other one's a little more straightforward and streamlined.
Matt, so on the test, I know there's one just like number 12. So could you do that one too?
All right, let's do number 12 too.
There's one just like this.
Okay. So I think I'm gonna do 13 first and then jump back to 12. Just so they can give it a little bit of time. So 13 is 2.5 e to the minus 1.2 x equals 1. 12 is 100 minus 5 times 10 to the x equals 7. I'll give you a minute to get started on 12, I think is what I need to do. Okay. If we want to do 13, I feel like 12 is harder than 13 anyway. What is
It's got that extra step on it.
Until it does.
2 extra step. Yeah, 1 extra step, but it's a big one.
What am I doing in 13? What do I want to get by itself? I want to get my exponential thing by itself. So you see this thing right here, that's your exponential function. You have a number to another number. You don't want any other number there. You don't want any other constant out in front. What am I going to do?
Move the coefficient to the exponent.
That works with logarithms.
Hmm.
I want to get that thing in red by itself. So what does
Pretend
that?
like that. What he's underlined is just like an X. How would you get rid of the 2.5?
Oh, you just divide by 2.5.
If we
Okay.
divide each side by 2.5,
Okay.
that 0.4 or 2/5, I think is what I'm going to get. If I simplify the fraction, I think I'm just going to go with the decimal. We do 1 divided by 2.5, I'm going to get 0.4. Okay.
But if it wasn't exact, what would you do? I mean, I'm just curious as to, I mean, I'm not going to count off for something really small, but
Oh,
If
like
it
1
wasn't-
over 2.5, is that what you're saying?
yeah, if it wasn't exact, you would leave it.
Yeah, you would have to multiply
yeah,
top and bottom.
Because you don't want to round to the very end. Not that I would count off for that, but
Is 2/5 or 0.4?
Yeah.
All right, so we get e to the minus 1.2x is equal to 0.4. What's my next step here? I have my exponential by itself. That's the first step. The next step is to do it. I want to get rid of this. Get them alone and pick on them. How do I get rid of them? It is, sorry,
Put an L in.
it is ln. This is an e or base e. It's a natural exponential. To get rid of them, we got to get an ln. Okay. So what's happening on this left side? What am I getting out of this left side over here?
Negative 1.2x.
Yep, you did that for a reason. You did that to get that thing by itself. This is ln of 0.4, whatever the heck that is. It's some crazy irrational number. I'm just going to keep it as ln of 0.4 for now. I want to solve for x. We're almost there. My x is going to be equal to I'm gonna have ln of 0.4, and what am I gonna do? What's the last step?
Divide.
By
Negative 1.2.
Yep, that's it. And if I want an exact solution, that's my exact solution. If I want an approximation, let me do that right quick. Minus 1.2. It might be worth noting that we're getting a positive number out of this thing because we're doing a log of a fraction, gives you a negative number. This is giving me a negative number, so I'm getting somewhere around 0. Let's go what? 764 if I round it up. If I do 3 decimal places, and I should be doing approximations.
And another thing I just want to say, if we're asking to the near thousandth or whatever, I don't usually count off if they like it. It really is more correct if you put 0.764, but if you put 0.763, I'm not that picky about that kind of thing. So.
Yep. Okay, questions about this one? So the approach is to get the weird thing by itself, right? And once we get the weird thing by itself, we undo the weird thing with the properties we just learned what's in the last like 3 classes, right? Okay. And then we're solving what? First order linear, basically after that. Okay, so that is what? 12 is the next one. So what is next? What is the first step I'm doing on this thing? 100 minus 5, 10 to the x equals 7. What's the thing I want to get by itself? What is my exponential here?
10 to the x.
Just a 10 to the x. Everything else needs to go to the other side. So we're looking at that. This is just like a variable. So if it helps to look at this just like a variable,
We could start by subtracting 100 from each side.
that's exactly what we want to do.
A really, really common error is, this is why I wanted Matt to do this in particular, is a lot of people will forget PEMDAS altogether and subtract 100 minus 5 first. Then that's just everything from there on out. It's just wrong.
And so this side, we still have this thing here. This is a minus 5. This is a 10 to the x.
Divide by -5.
The next thing we have to do is look at this like it's a variable. We have to divide by a -5. So 10 to the x. If we divide negative by negative, it becomes positive. I think 93 over 5 is probably fully reduced. It's not a pretty thing, but there you go. I think it's an even fraction though too, if you want to do 18.6. That would be fine. All right, so we did the dirty work, I think, on this one.
Log both sides.
I've got to log both sides. After we log both sides, I think that's not a lot more to do after that. If I log the left side, what am I getting?
1 second. 6. Let me see here. 1.26 or 1.27.
Are you doing log? Oh, you're doing log of the right side. No. I said log of this side. What do I get out of this?
Oh, X.
Yeah. This is just giving me x. All right. This is log of 93 over 5. If I want an exact solution, that's it. If I want an approximation, it's that thing that you just told me, 1.27?
1.27.
Yeah, round it up a little bit. That's it. Questions about this one? So it's really about getting your eyes adjusted to seeing just the exponent, the exponential function by itself. You look at that just like it's a variable, like just like a first order linear equation, right? We're gonna have to subtract we're gonna subtract the 100. We're going to have to divide by 5. After we do that, we have our exponential by itself. We do the things that we just learned to get rid of our exponential, which is taking a log. So in these, we got exponentials and one more exponential. And then we're going to jump to things that are logs. Ooh, this one's got 2 exponentials in it. All right. 31's a bit tricky. Give it a try though. That's what I say. These two, and then I really love the word problems on this one. But I think, like, to be fair, I know that word problems seem like some dark shadow that you never want to cross or something, but like they're going to give you an X value or they're going to give you a Y value. You're either going to solve it by directly plugging in your X or you're going to plug in your Y and you're going to back solve it. Like there's 2 basic sort of things that you're going to do for the most part. There's one really confusing problem that we'll work on in the homework and probably nowhere else. The temperature one. I don't know if you noticed that one.
Oh, yeah, that one. Oh, no, I
crazy.
did. And when I used to tutor in the lab, that one was always the number one
Yeah,
problem.
I'm gonna have to open up my book for that one because I was like,
Me too.
I definitely don't know that off the top of my head.
I know. And they could give you some warning, like, you know.
So this example or something they're gonna tell me, but no. Just here it is. Good luck. All right. So 31 is a bit weird. What'd y'all do to 31? There are like 2 different things you could do, at least that I can think off the top of my head that would be correct. We have an e to the x minus 3. This is my exponential on this side. Oh no, you notice there's another exponential on this side. So I don't think we're going to get rid of both of them at the same time. But did y'all try to do anything to get rid of one of them? And what'd you do? I'd probably just read it left to right. I get rid of that thing.
You can't just move one of them over and then make it equal to 0?
I mean, you can, but I'm not sure how that's going to help you solve it.
Hmm.
I'm not seeing.
How would you get rid of that E?
Yeah, if we did this, we'd have to subtract 2 to the 3x equals 0, and I'm not sure that that would be easier to solve.
Hmm.
The strategy generally is to get your exponential by itself. This is by itself. If we wanted to get rid of this, we could do that. This is also technically by itself, so that would also be another way to get rid of that. But if we want to get rid of this, how would we get rid of E?
ln.
ln.
Yep, taking an ln, a natural log of both sides. If we do that to the left side, what's happening over here in the left? What is that spitting out?
X minus 3.
Ooh, hopefully. This is ln, I'm going to write it out, 2 to the 3x. This side looks pretty good. This side, I have this thing up in my exponents, and I don't want this thing up in my exponents, right? Is there something I know about this to where I don't have to get it up in my exponents no more?
And you could actually just do it with the x, right? Because 2 to the third is just 8.
Yeah.
I mean,
Yeah, I mean, there's multiple ways to do this.
I mean, I would add a 3 to both sides first just to make x equal to something. Maybe start it out that way.
If you want to, I think that might be one approach. I'm not sure. Close. ln 2 to 3x. I'm not sure if that's going to get us in the direction we want. What can I do with that thing? What properties do we know that we've learned recently? If it's in the exponents in a log, what can I do with that thing?
So you can pull it down and put it in front of the log.
I can pull it down in front. So this is x equals what? 3 plus 3x ln of 2. Is that what I'm doing? Okay. Now this looks really weird, but this is just all a coefficient on x. So we really have, if you look at it, this is first order, this is first order. It's a first order linear sort of equation sort of thing happening. We're solving a first order equation. The strategy is to get everything with an x to one side and everything without to the other. How would we do that? This has an x. This does not have an x. This has an x.
So we subtract the 3x.
So we want to subtract this 3x ln of 2. So if we subtract 3x ln of 2, we can move it to the other side. And this is equal to 3. You might want to put a coefficient of 1 here. So the strategy to solving a first order linear equation is to get the variable to one side. Everything on the side has a variable. So the next strategy, does anybody know the next part? This is usually the thing that trips people up, I think. This is usually the hard step that I'm just curious. Anybody know it?
Mm.
They both have an X in there, so what can I do?
I mean, you can't just subtract them because the 3x is attached to the ln of 2.
Yes.
But let's see if we take ln of 2.
What happens if we take what? If they both
ln
have
of
it in
2
there?
is like 0.693.
I don't want to round this. I'm gonna keep it exact until the end.
Oh,
So what can I do if they both have it in there? Not distribution. We want to go the other way.
1 minus 3.
And there's also a ln of 2 on that one. And this is equal to 3. This is looking really kind of funky, probably. But we have this thing. We have an x multiplied by this crazy thing here. And it's equal to 3, the last step. Does anyone see it? It's a bit crazy, but it's there. If this is multiplying, what do we have to do to get rid of it?
Divide.
Divide by crazy thing. So 3 over the crazy thing, which is 1 minus 3 ln of 2. So if we want an exact solution, that would be an exact solution. Ooh. If you want to approximate this, this is 3 over 1 minus 3 ln of 2. I'm getting a negative number, negative like 2 point, if we round it up 7, 8, somewhere in that ballpark. Any questions of this? This one is pretty involved. So where do we start out? If it has two, but I think the approach are like is something you might be able to take away, right? If it has two exponential functions, take care of one of them at a time. If we take care of the left side, we can bring this thing down in front. We're solving a first order linear equation. Get everything with the variable to one side. Once you have everything with the variable to one side, you should be able to factor it out and then do some division. Okay. 53, 63, 67. So we have 3 log problems. Hopefully you started on 53 already. So I want to give you a little bit of time to work on 63 and 67. If you haven't finished at 53, hopefully you're doing that. So the strategy is still the same as the sort of previous. We want to get the weird guy by itself, so get the logs by itself. And now instead of taking logs to get rid of exponents, we're going to take exponents to get rid of logs. We go the other way. So you might notice 53 has 1 log, it's already by itself. You might notice 63 has multiple logs, so you might have to use those log properties to combine logs. Same thing with 67. You might have to get those logs to one side, combine them logs.
This one comes out nice, thank goodness.
Does 67 would come out.
I haven't done 67, 53 comes out nice.
Okay.
Are we working on 67?
It is one of them on there. I don't think it comes out pretty.
53 does, but 67, I don't know about the other one.
I'm not sure we get it. I might be wrong. Looks like it's going to give problems with getting the solution there. Okay. We want to do this. And this is a pretty good first sort of example. They have one log by itself equals a number. So how are we getting rid of a log base 2? And it's a weird thing to do, but I did it in the notes. I want to look at this like it's a what?
Exponent.
Like it's an exponent, and what would my base be then?
2.
It would be a base of 2. So this is like an exponent on a base 2, and this is like an exponent on a base 2. And so maybe there's like a little bit of argument to be had that like if this is the same base, these have to be the same exponents for the number to be the same, right? And there's something with the way that we break down numbers and prime factorizations and things of the like. Prime factorizations are unique, right? So we know the exponents would have to be the same. Okay, so what am I getting out of this left side over here?
X minus 2.
I'm getting the 3x minus 2 out of this left side. On this right side, I have 2 to the 4th. 2 times 2 is 4 times 4 times 4 is 16. So 2 to the 4th we can crunch as a number, it's just 16. You know how to do fourths? They're squared squareds. Do 2 squared and square that. Can you solve 3x minus 2 equals 16? I hope so. We should be getting what? X equals 6. Okay. Questions about this? And I hadn't done
It
it,
turns out really nice too. It does.
but we should probably really be checking these solutions, especially when we start plugging them into logs. If we have a log base 2, and this should work. 3 times 6 minus 2, is that equal to 4? Is log base 2 of 16 equal to 4? It should be. 2 to the 4th is equal to 16, so I believe that checks. Okay. But remember, our logs do have those domain restrictions of x has to be greater than 0. So it is good to sort of check these things. We can also check that this is a number greater than 0, right? Or actually 3x minus 2 would have to be greater than 0. Sorry. The thing inside the log would have to be greater than 0. Okay. 63 and 67. So I gave you a little bit of a hint, but what do we have to do to log of x plus log of 2x? We have to combine them somehow. How do these two things combine? So we're going to combine them to a single log.
Oh, okay, log of 3x,
Be careful now.
would that be it?
It's addition on the outside. What's the operation when we put it to one log?
Multiplication,
Yeah, so we're multiplying x and what?
2x,
2x. So this is log of
2x squared.
And this is equal to 2. All right, so now is the weird step. We got the log. It's a single log. We got it by itself. There's nothing multiplying it out here. There's nothing adding or subtracting. This is, if we got to put it, it's a log base 10. So how do I want to get rid of this log is the next question. That's the thing that's tripping me up here. Let's get rid of that guy.
Exponent base of 10.
Exponentiate it as a base of 10. Okay, so this left side is giving me what now?
2x squared.
We did that so that we could get the 2x squared out. This right side is giving me, ooh, now be careful. So people see, like, I don't know what it is with the exponents and people trying to multiply things. But this is what?
That is 1024.
Here?
Yeah, 1024. 2 to the 10th power, I got 1024.
10 to the second.
It's the other way around. Yeah.
Oh, 10 to the second power, okay. So that's 100.
Yeah, the base is 10, the exponent is 2. 2x squared is 100 is what you said? That's right.
Yeah.
So what are we doing to solve this thing? And there's a few ways.
I divide by 2 first.
Yeah, so x squared equals 50. That's probably what I'd do. And x equals, oh man. Please tell me this. I'm gonna cry a little bit if no one says it.
It doesn't come out nice. I was hoping it did.
How many solutions should we be getting for this thing if it's a square?
Square root.
We should be getting 2. One of them should be what? And one of them should be what?
Oh, plus or minus?
Plus or minus. And we're doing what to get this thing? Well, I'm already writing it. Square root, right? Square root property, taking the square root of both sides. If we take the square root of both sides, we absolutely have to do plus or minus root 50. I think it's a 25 and a 2 if we want to break that apart. I'm seeing a square root of 5 in there, basically. A 5 coming out of there. Square root of 25 is pulling out 5, sorry.
Matt, can we take just a second and let me show how I did it? But just so they can see how different the approaches are, it'll take just a second.
Yeah,
I just want to say, I just want to show how I started it.
I think we can reject the negative solution though, right? Because if we go try to plug a negative back into our log, it's going to give us an error. And so we really only need, I believe, the positive solution out of this thing.
Yeah. So when I started it, I don't get a quadratic. And this is what I just wanted to show them how different things can be. Because what I did is I split up that log 2x. So I started with log x plus log 2 plus log x equals to 2. So it didn't turn into a quadratic. So that's just a different approach.
Do you want to share your screen? Or
Oh, yeah.
I was going to
Well, no, you don't have to. Just you don't have to. I just wanted to tell them that there's different approaches that sometimes my answer would still come out to be, well, actually, I'll show you what my answer turned out to be, and really ugly. Now, let me show my screen real quick. I'll just show you. It's super ugly. See, I took that, the log x plus log 2x, and I split that up to be log x plus log 2 plus log x, because that's, and then I got 2 log x is 2 minus log 2x, and then then I get this ugly thing for my answer. But it should turn out to be the same as what Matt got if you turned it into a decimal. Let's see if it does. Because these would cancel out, right? That just turns out to be a half. So I must have done something. Anyway. Oh, this is 2 minus. Never mind. So
Yeah, I don't think you
that
can.
wouldn't cancel out.
Yeah, you can't.
It's not
multiply
multiplying.
the two
Yeah.
out there.
Yeah, that's totally wrong. So let me see. So 10 to the power of 2 minus log 2 over 2. And that gives me 7.071. And the square root of 50 is the same thing. This is the same thing as the square root of 50. So your answers could look totally different. And that's why, so.
I think you're missing a divide by 2 on that thing, on that second one.
No, because the divide by 2 is in the exponent.
Yeah, and so it still should be having a divide by 2 on there, right? And second exponent?
Right here?
Yeah, and second
Oh,
exponent.
yeah. Oh, I see what you're saying. Oh, no, I divided. Yeah, okay. So what I did, and I'm just doing things crazy. No, I did. You're right. I did divide it by 2. 2 minus log 2 over 2. Yes, that's right. And that gives you 7.07. And the only reason I wanted to show that is because it's really hard sometimes to grade these because people do different things. So that's why it's important that you are able to use your calculator so you can show your approximation.
Okay. And the last one, 67. Okay, so how will we combine these logs?
Multiply them together.
Multiply them together. So there are multiple ways you can do this one as well. I just realized at least 2 ways in my head. 3x minus 1 equals ln of 10. If I want to combine these, I'm multiplying x. And this is probably where you got to be careful because you're multiplying x by 3x minus 1. There is going to be some distribution there.
And another thing, if I was doing this, and again, I would immediately change that. No, never mind. Go for it.
Yeah, I would distribute this probably right off the bat.
Yeah.
And there are multiple ways to do this. If you wanted to combine all logs into one log, that is an approach to do this. There is a really cheap trick that I was like noticed. If once you have it here, you actually don't have to do that. This is an ln. That's an ln.
Exponentiate e.
If we exponentiate both sides to e, we can actually get around moving that log to the other side. And hopefully this makes sense. If we have something in an ln and we have something in an ln, guess what? This thing, 3x, minus 3x squared minus x should be equal to this thing. We're plugging them both into the same function. The numbers should be the same, right? If you move this one to the other side, you would have a side of 0, and when you take an ln of 0, you're going to get 1, and this thing would be divided by 10. you'd end up moving that 10 to the other side, probably first step anyway. So I think this saves you like maybe like one little step. All right, so we have this thing. How do we solve something that looks like this? What is this thing? So far, they've been first order. Now we're getting to what sort of function? What sort of equation is this?
Square root.
What? A square? Is that what you said?
Yes.
Yeah, square function or a quadratic. So how do we solve a quadratic? Oh, gee. Have we ever done this before? 3x minus x minus 10. We set one side equal to 0 and try to solve it. So what is that? Minus 30. What is that? 5 and 6. I think it breaks up into 3x squared minus 6x plus 5x minus 10 equals 0. Group and factor. I'm going to factor out what? 3x. That's leaving me with what? X minus 2. I'm going to factor out 5. That's going to leave me with an x minus 2. So maybe I'm going a little bit quick over these, but I think we've done a few of these at some point in this class. So I get my factors. I get my solutions. This is going to give me x is a minus 5 thirds. It's going to give me x equals a positive 2.
Matt, I'm supposed to be giving Letty a test right now, but I can't put us in another room. For whatever reason, can you put us both in a separate room?
I think it's going to break everyone out if I do that.
You can just pick me and her and put us in another room.
Fine, man.
It gives you that option if you're the lead person.
Let's see.
Awkward. Oh goodness, I'm a horrible. It's okay, she's my teacher.
Okay, I think I did that. I think you can join since you're a co-host. I think
Okay.
you have the option.
Okay, thanks.
Okay. So, questions on this one? Which of these work? That's the next thing we need to look. So these are solutions, but AKA potential solutions, not bona fide solutions yet. How do we see if they work? We have to go plug them back in. Right away, I'm just going to say it. This one's not going to work. Can y'all hear me? Hello, hello.
Yes.
Okay.
Can hear you.
All right. So why am I saying that one's not going to work?
That's negative, and we can't take negative logs.
It's negative, and yeah, right here, I already have an X in here. The first thing I plug it into, it's already not going to work, right? That's what I'm saying. This one, I think.
I can't put myself in the other group. Can you put me in there?
Let's see.
Sorry.
Oh, there you are. I see you now. Assign to. There you go. Okay. That one, when you plug it in, it should work. I'm not going to go check it, plug it back in. So we have 5 more problems left. They are word problems. Half-life of Facebook links. So they're giving us this function to find out F is the percentage of hits and T is the hours. So F is giving you the percentage of hits or engagement after T hours after it's been posted. This is what it looks like. So determine the length of time T when 10% of the engagements are remaining. So I know they have a bunch of word problems, but basically, for the most part, I think they're going to give you a function, and they're going to either give you a y or an x value. So if they say 100 and 1/2 over 3, if we're looking along here at this thing, and they tell me 10%, is that giving me the f value or is that giving me the t value?
That'll be the F value.
That would be the f value, and I think they're giving it, I hope they're giving it as a decimal. I could be wrong. Maybe not. Because they're
Isn't-
starting, no, they're not. They're giving it at starting out at 100%. I can see it here. And it's going to half every like 3. T is in what? Hours? I think that's what's happening. I believe they're giving it just as a whole percentage. So that's not super obvious from here. Typically when we work with percentages, like it's really common to convert them to decimals. So that's a bit confusing. So they're basically going to give you an X or a Y value. Hopefully they won't give you something that's as weirdly defined as this. But it's a possibility, I guess. So we want to solve this. What are we getting by it? The weird thing here, it looks like we have an exponential. So what is the exponential I want to get by itself?
T.
This T is an
I mean-
exponent being divided by 3. What's the
Yeah.
base on this thing?
The base on it.
The base for this exponent.
I
1/2.
I'm looking for the base in the exponent right here. This is my
Okay.
exponential. This is what I'm trying to say. That is the thing I want to get by itself.
Divide by 100 first.
I have to divide by 100 first. So I'm dividing both sides by 100. 10 over 100 is what? 1/10. This looks like it's 1/2 T divided by 3. So I have an exponential. I have it by itself now. How am I getting rid of this base of 1/2?
Take a log of 1/2.
Take log of base 1/2 of this thing. And I'm taking log base 1/2 of this thing. And these will give you even decimals. If you want to do 1/2 is 0.5 and 1/10 is 0.1, that would also work on this one. It might be easier to type into your calculator than typing it in with the division bar. Sometimes the decimal is a little friendlier, right? Okay. So this is a crazy log thing over here. But we have a calculator, so hopefully it's not too bad. We can do it in a calculator. This thing is giving me what over here?
T divided by 3.
Yeah, and it's all kind of crammed in here. But these two things should be the things inversing themselves. So I should be left with that t divided by 3. Now there's probably one little thing I need to do. If this is dividing by 3, how do I get rid of that?
Multiply by 3.
I gotta multiply by 3. So t looks like 3 times this thing, which is 3 times log of 1/2 of 1/10. And I think these, like I said, might be easier to put into your calculator if you convert it to the decimal. Although it shouldn't matter as long as you type it in correctly. So you might have to do change of base. So you might have to do change of base is log of 0.1 over log of 0.5. And if someone asked you this question and they were like, how long is it going to take this post to reach 10% engagement? And you told them 3 of log 0.1 over 0.5, they're probably going to look at you like you're kind of funny. So for problems like this, we probably want to round. So this is giving me somewhere around 9.97, I think. And so this is the number I'm getting. Does this answer the question? What are they asking? What is the time it will take to get that engagement? If I'm being honest, and it took 9.97, I'm probably going to tell this person it's going to take, what, 10 hours? Probably going to round that up just to 10, just so they're not mad when it reaches like 9.9 or something. We're literally 0.03 hours away from a full other hour, right? It's not a whole lot. Questions about this thing? So I don't think this is a whole lot different from what we're doing with just solving the things, right? They're just adding an extra step of words. And now we're either plugging in an X value or we're plugging in a Y value. Moore's law. According to Moore's law, the number of transistors that can be placed on an integrated circuit has doubled every 2 years. I'm glad we're going over this one because I was looking at those exponential homework. And there was a little something like everyone was missing, it looked like. And I think this one probably gets at it. So according to Moore's law, the number of transistors that can be placed on an integrated circuit has doubled every 2 years. In 1971, there were only 2,300 transistors in an integrated circuit. Find an exponential function, t of x equals c(a) to the x. That gives the number of transistors on an integrated circuit x years after 1971. So it's a little tricky, and I feel like they're completely misleading you on this one, if I'm being honest. We want a function that looks like this, that finds the number of transistors after x years. So c is like our y-intercept. What value am I going to plug in for c? That's like our starting point.
2300.
That's going to be the 2,300 transistors that I'm starting with in 1971. What is my base of? My base is 2. I want to double things. And if you say 2 to the x, guess what? There's one little thing you got to account for. We want to double it every 2 years. So how do we multiply 2?
Oh,
Every
2x?
We want to do something with this x. So we want to for every multiple of 2 here, we want to double it, right? So like if this was 2 years, we'd multiply by 2 once. If it was 4 years, we'd multiply by 2 twice. And so in order to do that, what we're doing is we also have to divide this thing by 2. So this is coming from the fact that it's doubling. So I know I have a bunch of 2's. But that's coming from the fact that it's doubling. And this is coming from the fact that it's every 2 years, right? So that after 2 years, we would have 2 over 2. We would be multiplying it by 2 once. At 4 years, we'd have 4 divided by 2. We'd be multiplying it by 2 twice. So this was sort of like that half-life problem we had in the homework too as well, right? It was like we have to divide it by the half-life length. So that every multiple of the half-life, it gets multiplied by half, right? Now we're doubling it. It's going to get multiplied by 2. You're on mute if you're trying to say something.
Matt, could you put me and Monica in still another room?
I have a room too. Where is she? Move to 2. Okay.
Thank you.
We still had you hiding in room 1. Okay. Okay. So if they said it doubled every 3 years, how would I change that?
X divided by 3.
X divided by 3. Right. Okay. So if we evaluate what, T of 40?
I didn't get put in another room. Can you put me in there too? I'm being very annoying today.
Says you're in room 2. I can try to move you back and forth. You should have the option to join, I hope.
I don't.
Well. Oh, go in there. Is it not giving you an option to join?
No.
Could you host a new one, maybe? Like host a separate Zoom meeting? I don't know how this works. I'm not used to using Zoom.
I know. I am. No. Okay.
I have to close the rooms because I only have 2 rooms, and I have to close the rooms in order to open more rooms.
Oh, you would have to close. You
Yeah.
only have 2 rooms? You have one open with Monica and one open with Leticia?
Yeah.
Okay.
It'll also probably make you hosting and probably be easier. Let's see. I hope
You
this
make me
doesn't-
host and then you can put yourself back as host. I'm sorry.
See if that works.
All right. Thank you.
Hopefully that, it should still record my. Okay, so we want to do T of 40. So are they giving us an X value or a Y value is my question.
X value.
They're giving us an X value, which our X value, I believe, is the years, right? So if we do this, this should be a straightforward crunch calculation of some sort, right? We're going to take 2300. We're going to do 2 to the 20th power. Is that what we're doing? 40 divided by 2 is going to give me 20. Ooh, we're going to double it 20 times is what this is saying. Times 2300 gives me a ridiculously huge number. Let me start from the back. 800, 724, 411, and leading with the 2. Was this 1,000 million billion, right? 2 billion.
Yeah. Sounds about right.
411 million. Yeah, it's probably what we expect for an integrated circuit nowadays. Is about 2 billion.
Yeah.
So what is that telling me?
There's a lot of those little connections, the gates is what they call them.
Yeah, so 40
Circuit.
represents what again? So 40 represents years, where does it say it? X years after 1971, right?
Yes, because B is evaluating 40, so that'll be 40 years after 1971, which should be 2011, I guess.
40 plus 1971 would be what? Yeah, 2011. In the year 2011, there will be, or there are, this 2 billion number. And what do those represent? Again, what did they say? Transistors on an integrated circuit is what we are talking about. Circuits.
Of course, I don't mean to bother the class here, but the laws of electromagnetic science are starting to reach their limits with these chips, the way they're designed. So they can only do so much with an electron in a little tiny circuit.
Yeah, I was about to say
So,
we're
sorry.
limited by the size of an atom or electron. Yeah. Yep.
Right. So basically, the next step is what they're building now. They're still in the sort of the experimental phase. Are these computers that are called qubit computers that they use the laws of like string theory and stuff, basically to create this type of qubit, which is a 0 and a 1 at the same time. And these are called quantum computers. So they use quantum mechanics. And the rate that those computers are going to grow at is going to be like the difference between Moore's law, which is like multiplication. You double every 2 years. This is going to be going up as an exponent. Like it'll be like cubed or squared every 2 years or something like that. It's going to be ridiculous amount of growth each generation of those microchips.
Sounds promising. All right, so this is part C. So we did part B. Part C says something about what now? Determine the year when integrated circuits first had 10 million transistors. So what do we want to do? What is what? What are they giving us here? If they say 10 million transistors, where can I plug that in?
For your T value.
For my T value, so now this is 10 million. This is 2300 and 2 to the x divided by 2. So what are the steps here to solving this thing? It's not the prettiest thing, but it's doable.
Divide the 10 million by 2300.
Dividing both sides by 2300 is the first thing we want to do. We want to get this exponential thing by itself. This gives me 43, 47, 826. 43, 47, somewhere in this ballpark, 826. 2 to the what? X over 2. Yeah, there's not a lot of ways to simplify that fraction. You can take off 100 out of each of those, but that's about it. It does not simplify very well, so I'm just going to round it, probably. It goes close enough, hopefully.
Take a log 2.
I want
Both
to take log base 2 of both sides. Log base 2 of this crazy number. Should be the log base 2 of this thing, which you did that, hopefully. So that we could get the x over 2. We're doing log base 2 of both sides. And so this is x divided by 2, the last step. I believe is to multiply both sides by 2. I'm going to do 2. You might have to do a change of base formula. Let's see what it is, not rounded. Divided by log 2. So 2 times log, big log over little log. Are y'all able to plug this into a calculator and get a solution, hopefully? Ow. I'm getting somewhere around 24.17. And again, what does this mean? I believe this is what, years after 70, was the year 71? So I believe if we go 24 years after 71, that's what, 1995? It's a little after 1995. It's within the year 1995. 24 would be January 1st, 1995. 0.17 means a little bit into the year of 1995. In year 2. Oh, I can't even sing right now. My voice is cracking. Conan always used to have that like bit. In the year 2000. And then he changed it to the year in the year 3000. After in 2000s he couldn't use that. That was 90s Conan, I guess. Huh? Okay. Corruption and human development. There's a relationship between perceived corruption and human development in a country modeled by H of X. X represents the corruption perception index, where 1 is very corrupt and 10 is the least corrupt. Okay. Output of human development index is between 0.1 and 1, with 1 being the best for human development. They're giving me a crazy formula. Okay. For Britain, X equals 8. Evaluate H of 8 and interpret the result. So H of 8, I hope, is the straightforward 1.2n ln of 8. .3 plus 0.28 ln of 8 is giving me something like 0.88. And so the input is the corruption perception index. So a corruption perception index of 8 produces, what is this? The human development index. Okay.
Matt, I do not know why, but for some reason they kicked us all out of the breakout rooms.
Okay. Yeah,
Can you
can't,
put Leticia back into one?
I
and-
can't do anything because I'm not host.
Oh, sorry, I didn't mean to interrupt. Thank you for reminding me.
So a corruption perception index of 8 produces a human development index of 0.88. So that is a bit of information there. But it is a scale on like what, 1 to 10. This is a scale on 0.1 to 1. So what this means to you, I'm not sure, but there you go. The Human Development Index is 0.68 for China. Find the Corruption Perception Index. So in this one, they give us an X quantity. In this one, they're giving us what quantity? What should the setup look like?
Uh, 0.3 plus 0.28 ln of x equals 0.68.
Yeah, this is an h of x value now. So now we're setting this thing equal to 0.68. And we're back solving it. So 0.3 plus 0.2n, 0.28 ln of x equals 0.68 is the value that they gave us. And so now what is our goal? It's to get what, where? How, who, what?
Get ln of x by itself.
Get this guy by itself. So if you have to, look at this like it's just a single variable. There's two things we need to do. The first thing is
Subtract the 0.3.
subtract the 0.3 will give me 0.38. And then the last thing, ln of x equals what? 0.38 over 0.28. This one is not so bad. We get a single. You have to remember the definition. But x is equal to what? Do the circle thing if you want. Here.
Mhm.
I don't want to do 3, 8.
I did e to the power of 1.36.
Which is this thing when you divide it.
Yeah, that.
That's it. So we're doing e to that power. E to the 0.38 over 0.28. And so what does that give me? X is somewhere around, now I'm approximating things, rounding things, 3.885 is what you should be getting for this thing. And so what does that mean? That's the corruption index, I think, right?
Yeah, it spits out the corruption number.
This was the human development. This was the corruption number. Okay, questions on this thing? This thing is, it's a weird unit. It's a weird scale. They're going from one weird scale to another weird scale, if I'm being honest. But it's doable with the relationship that they give us, right? We should be able to do the math. You should be able to plug either into X or Y and solve for the other thing. The number E of E. coli bacteria in million per milliliter at 2 minutes can be modeled by, now they're giving us this model. This model is the number of bacteria after 2 minutes. Determine symbolically the elapsed time required for the concentration of bacteria to reach 25 million per milliliter. So how am I setting this thing up? What are they giving me and where am I plugging it in? That's the question I'm hoping you're asking. They're giving me 25 million per milliliter. Is that going to be a T or an N of T value?
That'll be the n of t value.
That'll be the N value. And what they want to find is T or time, 0.5 E 0.014 t. So I set this up like this. What is the first thing I gotta do here?
Divide by 0.5.
If we divide by 0.5, that's the same thing as multiplying by 2. We should get 50 on that side. I'm doing 0.014 with the t. Now I have this thing. I want to solve for t. How am I doing that? Ooh.
I'm taking ln off of both sides.
I take an ln of both sides. I take an ln of this side. That's ln of 50. That's a crazy number, but I can do it. This side should give me what? 0.0014 t. My ln, my e are inverse operations. If I want to solve for t, t is equal to what am I doing?
Divided by 0.014.
Yeah, dividing by that coefficient of 0.014, ln of 50 divided by 0.014 is what, 279.43, somewhere in that ballpark. And what are we talking about? T is that minutes here? What is it in? T minutes after T minutes. So this should be 279.43 minutes. Questions about this one? Okay, so warming a soda can. Suppose that a can of soda initially at 5 degrees Celsius warms to 18 degrees Celsius after 2 hours in a room that has a temperature of 20 degrees Celsius. And they give you this thing, and they tell you absolutely no way to solve the thing. But if you go back and look at your examples in your book, there is an example, and they teach you how to solve this thing. So T of T. Equation they give us of T equals not plus T naught is your room temperature. So this is the temperature after a certain amount of time. T naught should be your room temperature. So they say, suppose that a can of soda initially at 5 degrees Celsius warms to 18 degrees after 2 hours in a room that has a temperature of 20 degrees Celsius. So 20 should be my T naught. My D is my difference. So I got to make sure I do this in the right order. Difference between the coffee in the room or the can of soda in the room. So for D, I want to do the difference of my can of soda, which is 5 degrees. T naught is the temperature in the room. 2 hours, it's 18 degrees. How long did it take for 15? D should be the difference between an object in the room. So it should be 5 minus the room, which is 20. Make sure I'm doing this. Didn't read that correctly, right? Yeah, temperature of the room is 20. So my D should be minus 15. It should be negative. Oh, this is a mess. And my A, I don't know what my A is. I'm going to have to solve for A in that first one, I believe. That's a heck of a problem. I don't really like this problem, if I'm being honest. So we'll go through this problem. We'll do this problem. This is my formula almost filled out. I still have to solve for A. So they give me a little bit of information to plug into this thing to solve for A. So they say, suppose the can of soda initially warms to 18 degrees after 2 hours. So I have to plug in 18 and I have to plug in 2 to find out what the heck my A is. I hope that's not too hard. But we're going to subtract 20. Not the prettiest thing. So I think 2 over 15 is going to give me A squared. And typically when we do a square root, we want to take plus or minus. So I'm going to round it to positive. We only really want the positive part. This is not a pretty number. So if we want a function, I guess 0.514 to the t. And if we do 2 hours and we multiply that by minus 15 and we add that to 20, does that give me to the 18? Gets me to the 18. It's not pretty, but it will get us there. That is what the model looks like. So now they're going to ask us 2 different things. Can we plug in a time? I think the first one asked what time of 1.5 hours. Is that what it says? 1.5 hours. So can we plug 1.5 into t, into lowercase t, not uppercase t? So now we got to be really particular about the case of t that we have, 0.365148 to the 1.5. And if we plug in 0.365148 to the 1.5, and we multiply that by a minus 15, and then add that to 20, I feel like we're going overtime now. This is just like a really involved problem. And they don't exactly just give you the formula. You got to kind of go search for it in your book. But the temperature I'm getting here is 12.41 if I round it. The other way, guess what they're going to give? They're going to give a value for this thing over here. So now part 2 of this thing says we are going to 15 degrees Celsius, and we want to know how much time it's going to take. So now we want to solve this thing for t. This does look a little wonky. Maybe it's not pretty numbers, but this is still the same thing, right? We look at this exponential like it's a variable all in itself. The first thing I need to do is subtract 20. So I get minus 5 is a minus 15 times my exponential. Ooh, and now we're dividing by minus 15. This should give me 1/3 is equal to this crazy exponential. And now I have this exponential by itself. I have to take that crazy exponential So log base of this thing 365,148 of 1/3 should be giving me my t. So what is this log? And I do 1/3, and I divide log of 1/3 over log of 0.365148. Don't close it with that. Close it with that. It's around 1.09. I'm getting something around 1.09. Which means after what, 1.09 hours, I think is what it's saying. Hours or minutes? Hours. It'll be 15 degrees Celsius. Yes, that is a problem. It's not a pretty problem, but it's there. We did it for homework. You can tell everyone we did it for homework. All right, so let's look at the last thing we have on here, radioactive carbon-14. This is that carbon dating we did before. Percentage of carbon-14 remains after 2 years is this thing. So here we go, percentage of carbon. This one is a lot prettier. Let's do this one. T over 5,700. Suppose that a fossil contains 35% of the carbon-14 that the organism contained when it was alive. Estimate the age of the fossil. So what am I putting in for where they're giving me 35%? So where am I plugging that 35%?
Is that C?
It says P equals 100, 1/2 T divided by 5,700.
It would go where P is.
It should be a P variable, so I'm plugging in 35 into my P. What are the steps I got to do here?
Divide by 100.
Divide by 100. If I divide both sides by 100, I get 0.35 on this side. I'm just going to convert it to decimal. I get 1/2 T divided by what, 5,700? All right, so what's my next step? How do I get rid of that thing?
Log of 1/2.
That's the last problem we have to do for homework ever. Log of I can't even write anymore. See how happy I am? Log of 1/2 of this thing. Okay, so log of 1/2, I'm just gonna probably convert it to decimal because I can plug it into my calculator a little bit easier, and it's a good even decimal, right? So log of 1/2 is log of 0.35 divided by log of 0.5 is what I gotta do on this side. What is this side equaling over here? Scratch, 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 scratch.
T divided by 5,700.
Yeah, it's horribly written, but this should be T over 5,700. So T is equal to, I have to take what? What am I doing with these things?
Multiply by 57.
Multiplying 5,700 by log base 0.5 of 0.35. So I'm doing log of 0.35. I'm dividing that by log of 0.5, and then I'm multiplying that result by 5,700. What should this be giving me? Something around 1.5145, something like that, right? What is that giving me? Something in that ballpark, right? All right, so what is that telling me with the problem? I guess I gotta go back and interpret it. One last thing. Radioactive carbon-14, estimate the age of the fossil. So it's around what, 8,633 years old. Old.
I did have a question for 113. I think I might be putting in my calculator wrong because when I do 20 minus 15 times 0.365148 to the 1.5, I come out with like 16.69. I think you got like 12 something.
0.365148 to the 1.5 is what we're doing. 16.69 is what we said.
Yeah.
That seems correct.
Oh, okay. I don't know what I looked at wrong then. Okay.
Be able to do it piece by piece too, right? Did I say that a while ago, or did I say something else?
I swear when I looked up it said 12, but I might have been looking at.
I said 12.41. I think I miscalculated it. It looks like.
Okay.
Yeah, so good call. I did put the wrong thing there.
It's all good. It's been a day.
It is a long section. We are way over. But here we are. I'm gonna stop recording.